All right, get in there. So, that has been in use since 1973. You don't like touching. So last time we started talking about these power series, and they seem to be appropriately named because they're built off of powers of x. So we're working our way towards being able to do something like, this is our motivation for doing this kind of thing. A little motivation. If I can rewrite e to the x squared as something like 1, and this is not what it really is, so let's just say it's 1 plus x over 4 plus x squared over 16 plus. If I can rewrite that function as a polynomial that's actually infinitely many terms, right? And you can do this, and I'll show you. We already actually know how to do this directly. This is where we're going to kind of start. If I can do that, then if I had to integrate this thing, and this, of course, is your classic, you can't do that. Right? You can't do that. You can't. You got to do it numerically. But this is actually one way we could do it by hand, is to just integrate. And we just go out far enough so that our error is acceptable. So if I'm able to figure out a way to rewrite a function as some open-ended infinite sum of like a polynomial, then doing a lot of things like derivatives, integration, all those kind of things would be really simple. Believe it or not. You're like, oh yeah, you just got to become infinitely many terms, and it's simple. Thanks, Jeff. But actually, it's kind of cool. If I just stop at the right place, I can actually approximate values of that function pretty quickly, pretty easily. So I can, for example, take the square root, rewrite it as some polynomial. So if somebody asks me what's the square root of 11, and I just happen to know this approximation, I can just do it real quick in my head. Right? So we're sort of going in that direction. So we start just analyzing power series by themselves. So the very first thing we talk about in section 11.8 is something very important, which is, when do these series converge? Because if it diverges, it's not worth a damn thing. You with me? So if I try to write like sine x as some infinite sum polynomial type thing, and that guy diverges, what the hell good is that? Right? Sine x, what's the largest its output can be? 1. So I kind of want, and of course it's bounded below by -1. So I need to know, when does this power series representation, when does it converge? Because that's, of course, the area in which it makes sense. Outside of that, it don't make sense. So that's why we kind of start there. Get used to what power series themselves are, and then where are they useful? How do I figure out if they're useful at all anywhere? Okay. So I gave you a couple of specific examples, and the very first thing we want to talk about, like I said, is when does it converge? And we call this it's called the integral of convergence. And then somehow in there you get the radius of convergence. So we'll come back to these two when we have an actual concrete example to look at. Right, but this is going to be nice. Radius of convergence. Interval is going to have some center and go out. So of course the radius is going to be how much you go out either side. That's how they're connected to each other. Right? So it could be an infinite interval if it just converges for all values of x. So the one example we looked at last time was really, really easy. If I had this, we know already when this thing converges. Do we? What's got to be true? What kind of series is this? I know it's a power series, but even more specific, it's geometric, right? Because what's x going to be? What is x? A number. Kick ass, right? So it could be 1 over 7, in which case this would do what? What would this do, this series? Why would it converge? R is less than 1. Beautiful. So x in this case is r, right? X is our r here. R. So this was, I don't even have to do much work to know that this is going to converge if the absolute value of x is less than 1. We know that just looking at it, but let's real quick, we did this last time, but just to remind everybody, let's do one of these with a very simple example like this. How do I prove that's true? What test can I use? Say it louder.
Ratio.
Ratio, exactly. It's a good one for ratio because it's an exponential. It's a power, right? So if I use the ratio test, the one thing to be really careful about on the ratio test is what goes in the top. Yeah, the next term. So if you switch those, shit, you might be in trouble. I don't know. We'll have to find. So the limit, n goes to infinity, an plus 1 over an. So what's an plus 1 in this case? Yeah, x to the n plus 1. Over, and what's an? X to the n. All right, well, that's just too easy. Yeah, exactly. So this is the limit as n goes to infinity of x. And in order for this to work, and of course that limit is absolute value of x. Now don't forget your absolute values. The whole idea of ratio test is absolute convergence, right? Which of course explains where this would eventually come from. And of course here, what's the result's got to be for this to converge? The resulting limit has got to be less than 1, which captures what we already knew was true. We knew it was geometric. We knew that should be true. And thankfully, the test we want to use actually confirms that. Right? Now, the next level of this, and this is, some of what we're doing is kind of silly in this case, but just to show you the whole thing you got to do, you got to check the endpoint. So how can I rewrite this a little more fully fleshed out without the absolute value? How do you rewrite that? Negative 1?
There's the x. 1.
Good. Make your ones all the same, Jeff. So now I just have to take a second and check the endpoints. And that's a remarkably simple thing to do because all that means is you allow x to be an endpoint and just see what you get. So if x were negative 1, what is our original series then? If x is negative 1. Negative 1 to the n. Now what does that thing do? Does it converge? It just oscillates. Right? At first it's negative 1, and then it's 1, and then it's negative 1. So what's the sum doing? First it's negative 1, then it's 0, and then it's negative 1, then it's 0. Is it going to converge? No. Hell no. Of course the quick answer is the dang thing oscillates, right? Like a trig function. So this does not, how do I say it? Does not converge. If it did converge, then I can go back and make that like that. But it doesn't, so I just have to keep it out. And of course, if I put a 1 in,
straight line.
Well, yeah, it's not really a function that I'm graphing. But what would happen if it would just be 1 to the n, which is 1. And when you sum 1 forever, you get infinity. Right? So it's not oscillating this time. It's just infinite. But it doesn't matter. Either way you look at it, that thing does not converge. So if x is 1, goes to infinity, nope. So then that is my interval of convergence. What's my radius of convergence? What's the center of this? 0. 0's in the middle. So what's my radius? 1. So if they ask you for the radius, it's just going to be how far does it go out from the middle? Or you look at, that's 2 across, divided by 2 is 1. That's the diameter, cut it in half, you get the radius. How do we feel about this so far?
Pretty good.
Of course, that was a simple example so far. The work doesn't change. Just the level of difficulty of the function they give me changes.
I'm doing a complicated one.
No, I'm going to leave it. Yes, let's do it. Sounds like a good idea. Let's do, one, let's see. I want to say it's got a decent outcome here. Now don't forget the general definition of power series. This was a simple, well, it's gone now, but the one I had earlier had 0 here, right, for A. But A, of course, could be anything. So it could be x minus 2, x plus 7, whatever, right? But if I make A 0, I just get x to the n. So at the very top, the general power series looks like this. Coming in. That's what they look like in general. So in this case, can somebody tell me what's Cn? No. Cn is everything that isn't x minus a to the n. Yeah, so 1 over n. It's got to be 1 over n. So Cn is a constant that's a function of n. And of course, when you say this, like, no, then how the hell can it be a constant? But it's just a constant that changes as n changes. Each n makes it a constant. Does that still make sense? So that's why I call it C sub n. So C sub n in this case is 1 over n. Cool. And what's A? Just a 3. Amazing. Okay, good. Whereas the one we did earlier, A was 0. So how do I check this thing? How do I get the interval of convergence? What do I do? Apply directly to the forehead. No. Apply the ratio test, right? Ratio rest. Ruby root. Ratio test. There it is. So the limit n goes to infinity. Don't forget your absolute values. What goes here right now? What do I have to put first? N plus 1th term, right? So be real careful about that. Over. And then now we're to the point where we just, I know it's that over that, but it's times the reciprocal. Right? This one I didn't have to worry about it because they were just one liner, right? When it's a fraction to begin with, I multiply the reciprocal just to get to the point quicker. So what's going to be multiplied here?
And over x minus 3 to the n.
Yes. If you don't know where that came from, and you hear all these people that think they do, and they do, that wasn't everybody. So you can feel free to ask a question if you don't know where this came from. Okay, so that's a sub n plus 1, just putting n plus 1 in the expression, divided by, so that's where we reciprocated, an, which they're going to give you. Right? So ratio test is kind of nice. They're already kind of giving you half of it. So what happens in this case?
X minus 3 to the n.
Yeah, n of these cancel, right? And what's the limit as n goes to infinity of this? 1. It's to the first, so it's the ratio of the coefficients, it's 1. So any polynomial n squared n cubed piece, easy, let it be easy. Right? That's 1. So what do I end up here with?
X minus 3.
Absolute value.
Absolute value of x minus 3.
So that's the result of that limit. Is that cool? And of course, for the ratio test to be convergent, the result has to be less than 1. Kick ass. So you start to get the rhythm of these kind of problems, right? So that's got to be less than 1. So the radius of convergence, I can see it when I have x not being multiplied or divided by anything. So right there, the radius of convergence is 1. In fact, if you remember your algebra here, I'm going to go from 3, I'm going to go 1 up and 1 down. I want the distance between x and 3 to be less than 1. So I'm going to go 1 up and 1 down. Right? Of course, the other way to do this is say x minus 3 is in between what? Negative 1 and 1. So x is between 4 and 2. There you go. So it's 1 up and down from 3. So if they ask for the radius of convergence, it's 1. If they ask for the interval convergence, it's this. So this is the interval. This is the radius. Because x wasn't being multiplied. So if it was x minus 3 over 3, I have to first multiply by 3. And then the radius would have been 3. Or you just wait till you get here and you can kind of see it's the diameter is 2, so the radius must be half that. Either way you want to do it, that's how you can do it. A couple different options there.
So is the radius always going to be 1 then?
No. We'll do one where it's not. Because you're right, if you do too many of them, then everybody thinks it's always. But real quick, what the hell does this mean? We're not done here yet, but definitely if I let x be 5, what would happen here? It would diverge. And let's do it. If x is 5, I get 5 minus 3 is 2. 2 to the n over n. That's like just screaming at you, I am going to go to infinity. Leave me alone. Right? But if x were 3.5, 3.5 minus 3 is a half. 1/2 to the n. Well, that's a geometric. Well, r is 1/2, right? And the over n just helps it. Does that make sense? All right, good. Now, everything I just said was a little bit beyond the work you got to show, but it's the concept behind what you're doing. What do I still have to do? I'm not done with this. It's one thing I have to do. I know currently it's at least this, but what about the endpoints? Because the endpoints are where the ratio tests are inconclusive. But now I know exactly what x values are when it's inconclusive. I could just go check mine. It's like, thanks, ratio test. You got me most of the way there. I'm going to go take a look and see what actually happens. I know what one value is. I can make x2. If I make x2, what happens here? Ooh, I like this problem. So here, you set it up. I might ask you to identify these. Ratio test. You know the outcome has to be convergent. Solve for x. Then you got to check the endpoints. So if x is 2, I get -1 to the n over n. And all we care about is that series itself converges. Right? It is technically conditionally convergent, but it's not that series. That's the series we're looking at. So that, do I include 2 or not? Yes, this is convergent. So therefore I include 2. You stop there for a second. You plug the value in, that's the endpoint, because the ratio test doesn't know. Those endpoints would make this equal 1. And then the ratio test has no idea. But it's a lot more concrete than before. I can actually see the values that the ratio test isn't sure about. So I'm going to go, okay, dude, I got you. I'm going to go plug it in and see what the hell's going on. So when I plug 2 in, I get a series that converges. Technically conditionally convergent, but all we care about is this series itself converges. So 2, I can use 2. What happens if I try to put a 4 in there? Yeah, what does it become? 1 over n. Right? If I put a 4 in there, I get 4 minus 3 is 1 to the n is 1. I get the sum of 1 over n, and of course that thing diverges. P series, P is 1. Harmonic series, I like it. All these different names for the same damn thing, you gotta love. So this diverges. So the way it's written currently is correct. You can include 2, but not 4. Do you guys understand why we need to check the endpoints? The ratio test has no idea about them. But they're sitting there staring me in the face. So let me just plug them in and see what the hell happens. Sometimes they'll work. Then I got to go include it. Sometimes they won't. Then I'll leave it out. So I know that's how far, if I want to use this, that's how far my x values can go to keep this making sense. Maybe. Yes?
So, on both of those you use x goes between -1 and 1. Why was that?
Where are we at, sorry?
On both of those, yeah, that right there.
Yes?
How do we know it's just between 1 and 1?
Because at the very end, the limit I got was the absolute value of x. And no matter what the limit is, it has to be less than 1.
Okay.
Yeah. There, I got absolute value of x minus 3. It still has to be less than 1, but when I solve it, of course, that minus 3 moves me.
Okay.
It moves me over. Okay, all right, cool. I don't know if you can pick up on this, but this is some of my favorite stuff here. I'm hoping at least one of you feels the same way. We'll see. So here, you guys try the ones on the bottom of the handout. Trot those out. Don't forget to check the endpoints if it comes to that. If this limit had been infinity, what do you think? Is infinity ever less than 1? So what x values would work? Yeah, it's kind of interesting. The only x value that would work, like if this had come out to be infinity, the only x value that would have worked here would have been 3. Because that would make it 0 forever, right? So there's 3 cases in this, right in the middle of your handout. Either it converges for x equals a only, and that's when you get infinity as an answer. Or it converges for everything, and that's when you get 0 as an answer. Or it's conditional, depending on the values of x, and that's when we get stuff like this. You have an x dependence left at the end. Those are the only 3 things that could happen. All right, so you guys try the ones at the bottom there. Call me over if you need some help.